Hello my people, how are we today? This is video 1 on section 3.8 in your book, and after looking at it I'm starting to remember exactly why when I taught this course I would skip 3.8. There's no calculus in it. It's basically just and I wish that, not that I could see, not very much, if any at all. You can probably tack on a couple of calculus questions to the to the questions that are actually asked in the section, but the vast majority of it is basically what we did in Algebra 2 and Pre-Cal, and I covered this very well for y'all, so this should be very familiar territory. The only thing that they're really adding here is just telling you that these expressions, which we have understood sort of numerically and conceptually from the standpoint of what it means for an exponential to be part of a model for a scenario. An exponential is basically used any time that we need to multiply by the same number again and again and again and again and again. So if you have a population problem where the population of a particular city increases 3% every year, you're going to multiply by 1.03 again and again and again and again. What they're introducing here is they're saying, okay, well, these happen to be solutions, or these happen to be models which come from here. This is what's called a differential equation, and I think it's chapter 9 that deals with differential equations. You'll get there. But this basically says the rate at which y changes with respect to t is proportional to y, directly proportional to y, which is another way of saying, okay, if I said you have a petri dish full of bacteria, they double every hour, how many do you have after 5 hours? Well, if I asked you that question on a test, you would cry foul, because you'd be like, well, you didn't tell me how many I had to start out with, right? So the doubling has to occur with respect to an initial condition, right? That's saying that the doubling of bacteria, or the rate of bacterial growth, has everything to do with the number of bacteria that are already there. Because the rate is doubling, sure, but whether I have 1,000,000 or whether I have 1,000 at the end of 1 hour has everything to do with whether I had 500,000 or half of 1,000 at the beginning of that hour. So, it shouldn't be a surprise to us that a rate of change is proportional to an amount, like basically an output for this function. It's kind of like no matter when you stumble onto radioactive material, it is always going to be the half-life. It decays according to how much is left, and the half-life is determined, that the rate at which the half-life impacts the amount of radioactive material has everything to do with how much radioactive material there is at any time t. So all they're really doing is they're bringing it into orbit around calculus ideas without actually applying, at least not that I can see yet, without actually applying calculus to the model that we have over here. Now that being said, since you're going to be tested on it, it's worth going over a few examples for us. And again, I'm going to be going out of your book, so let's go ahead and get started. I'm going to be doing number 4 on page 243. A bacteria culture grows with constant relative growth rate. The bacteria count was 400 after 2 hours. Okay? So, bacteria, and we'll sort of draw a line right here, bacteria is 400 when t is equal to 2. Well, that's an ordered pair, right? When I input 2, I get an output of 400. Okay, well, the number of bacteria was 25,600 when T is equal to 6. So 6, 25,600, that is another ordered pair. Well, I don't have the initial condition, but I do have 2 ordered pairs. So remember, B of T is equal to B naught E to the K T. And if I plug in both of those ordered pairs, okay, I can actually find my K value. And my K value is, I think, what they're referring to as the relative growth rate, because it's the constant. This comes from the fact that the rate at which the bacteria increases is directly proportional to the amount of bacteria. Okay, so let's go ahead and do this. We have 400 is equal to B naught E to the K times 2, and then we're going to have 25,600 is equal to B naught E to the K times 6. Okay, now here's the thing. This is a system of equations. 2 equations, 2 unknowns, okay? And therefore you can do substitution in a number of ways. I'm actually looking for the fact that e to the 2k is obviously 400 over b naught. And this right here could be 25,600 is equal to b naught times 400 over b naught cubed, right? Because e to the 6k is e to the 2k cubed. This, of course, winds up being 25,600 is equal to, well, 400 cubed over b naught squared, or b naught squared is equal to 400 cubed over 25,600. And then, of course, you can solve for b naught from there. So it winds up just being a simple system of equations in order to find b naught. And then, of course, from b naught, you just plug it in order to find k. And you can plug it into either one of the original equations. That really doesn't matter at this point. That would be your k value, okay? And that would tell you how fast it's actually, increasing. Now, it says, what was the initial size of the culture? Well, you've already basically figured that out here, because in the system of equations, I just happen to solve for b naught first, so it doesn't really matter. 25,600, and that, of course, is, some decimal approximation. So that would be the answers to A and B, solving for K and B naught, respectively. Now, in part C, it says, find an expression for the number of bacteria after T hours. So if we need to find an expression for the number of bacteria after T hours, we simply need to take B naught and K and plug it back into here to have a complete model. And that's all they're really asking you for. And then, of course, D, E, and F are just plugging in. D is find the number of cells after 4.5 hours, so that's B of 4.5. This actually is a calculus question. Part E. Find the rate of growth after 4.5 hours. But you found K, and you don't actually have to differentiate. You could actually, just figure, like, since Part D gets you your B value after 4.5 hours, you could just plug in that B value into here and multiply it by the K value that you already know in order to get dB dt. So there's more than one way around that particular, around that particular question. So you actually, in Part E, don't actually have to use calculus in order to arrive at that answer. Now, that is actually rather instructive, because you will be surprised if you actually do stop, think, and before you do, on the AP exam, there's a whole host of problems that you don't actually have to use calculus in order to get the answer. Okay? And so we certainly don't want to shed and leave behind our understanding of those calculus, of those pre-cal and algebra 2 skills. Now, part F is basically an output-based question on the model once you've solved for K and B naught, and you know how to do that. Again, I'm somewhat limited by the fact that I do not yet have a TI-84, so I'm kind of explaining to you how to do this. But since we've spent weeks and weeks and weeks on this in past years, and if you're smart, you have not thrown away what I gave you, you should actually have all of this at your disposal. Let's go ahead and do number 8, which is a radioactive decay problem, one of my favorites. Not quite as fun as the ones that I write for my test, or wrote for my test. It's so hard to talk about my life as a calc teacher in the past tense. Okay, this is number 8. Strontium-90 has a half-life of 28 days. Okay, you should automatically think S of t is equal to S naught 1/2 to the t over h, which in this case is 28 days. Okay, that should be automatic. Part A says a sample has a mass of 50 milligrams initially. Okay, well, there you go. Okay, that's 50. So it's 50 times 1/2 to the t over 28. That ought to be really easy to set up. Now, of course, you can do the e to the kt thing, but if they actually give you the half-life instead of making you go chase after it by giving you ordered pairs or whatnot, then I say use the 1/2 to the t over h. It winds up being just a whole lot more straightforward. Find the mass remaining after 40 days. Okay? So basically, that was part A, including the 50 in there. So it's S of t is equal to S naught 1/2 t over 28, or if you like the e to the kt, you have 50 e to the kt, but then you have to go searching for t by actually using that ordered pair, right? Because anytime they give you the half-life, they're giving you an ordered pair implicitly, okay? They're saying that if you start out with 50, then after 28 days, you'll have 25. You'll have half of 50, okay? And then you would basically have to take this ordered pair and plug it in order to find K. That is a little more difficult than the original one, so I would just go with the original one. Now, part B says find the mass remaining after 40 days. Okay? Well, after 40 days, so you have an input-based question, meaning that you're being given an input, and you would just plug 40 in for t, and then you would get the decimal approximation. Now, part C asks how long does it take the sample to decay to a mass of 2 milligrams? Now remember, anytime you're asked an output question like this, you need to start thinking about it, okay? Because you have time and you have mass of strontium, right? At time 0, there's 50. At time 28, there's 25. At 56, there's 12.5, okay? Now, you do realize that after another 28, which is going to be 84, right? Yeah, 84, you're going to have 6.25, and then after another 28, you're going to have 3.125, and then after another 28, you have 140, right? You're going to have half of that, okay? So you're going to have a little more than 1.5. It's going to be 1.56, whatever. 1.56, Okay. Mainly because I'm tired and don't feel like doing that in my head. Obviously, 2 milligrams is somewhere in between those two measurements. Okay? So, you know ahead of time the range, the interval in which your answer should lie. So if it asks you how long does it take for the sample to decay to 2 milligrams, that is obviously an output-based question. You are to solve for t. So you have 1 over 25, 1/2 t over 28. And you know me, I always default to natural log. So I have natural log of 1/2 is equal to t over 28 times the natural log, or that's supposed to be 1 over 25 over here on the left, 1/2. And therefore I have 28 natural log 1 over 25 over natural log of 1/2 is equal to t. And that t value, and I don't, like I said, I don't have a proper calculator right now, that t value should be somewhere between 112 and 140. And I would suspect it would be closer to 140 because 2 milligrams is closer to 1.56 milligrams than it is to 3. Okay? And that is going to be how you're going to work that out. All of that should be very, very familiar. Okay? We have done a population problem. We have now done a radioactive decay problem. I think you know what's coming. In the next video, I'm going to do a Newton's law of cooling problem and an interest problem. That ought to sort of round us out for exponential growth and decay. I would go back and check your notes, check the tests, check everything from last year and the year before, and sort of work back through some of those problems. But that is the basic gist of what's going on here in 3.8. Little to no calculus at all. And like you saw on that one question, there was a way around doing the calculus. One more video probably, and then I will start trying to move towards getting related rates videos up and running, because that is going to be the real beast of it all. But I hope this is helpful, guys.